Okay, before you start, let me share my screen. I want to
Okay.
show something. So this is what I was talking about in class today regarding Blackboard. I guess it just doesn't want to work. That is really annoying. Okay, it's not the browser. Yes, Blackboard is not working right now. All right, so be it. Let me unshare.
Yeah, it's not loading from me either.
Yeah, I'll try again at the end of the lab. Mostly, I just want to show a link that's on a page that regards the design project team selection. I described it in the lesson today. If you go to the home page of Blackboard, assuming you can get to it, there's a link to the current teams. Only one team has submitted names, and so there's a bunch of y'all that still have to put together a team for the semester project. Okay, that's all I'll say. Josh, it's all yours, and make sure the recorder is running. The recorder is running. So go ahead and take them on a trip through the world of regression.
Okay, we're gonna regress today. Haha. Can everyone see my screen, and does it look all right? Because I'm putting it on my portrait monitor.
Well, I can see it. It looks a bit on the small side.
Okay, how about this is the normal view? Does that look better? Oh, I paused it. Try now.
It, so all you students that are in the lab, you probably should answer them, not me.
Yeah. It's not a big deal. I just figured I use my portrait. I don't think I can hide. Oh, there we go. I use my portrait laptop portrait monitor for coding, so I figured it might be useful, but it's not a big deal. Okay. So today we're going to be talking about different methods of regression. The most common one that everybody needs to know, at least over in CS, is linear regression. It's the most basic kind of pattern prediction algorithm there is. It's very simple. It's just put a line through your points on your graph. Oh, Blackboard just came up. Put a line through your points on your graph and pick a line. And how can we measure when one line is better than another? What do we even want to use that line for? Well, let's look at some real life examples first. So the human brain is amazing and mysterious in many ways. This reminds me of a quote. I actually looked it up because I learned it from Civilization 4. No, Civilization 5. It's this one here. It's, if our brains were simple enough for us to understand them, we'd be so simple that we couldn't. That is, I think about this one a lot, especially when we get into something to, it's like, man, how do our brains even work? If we could understand how they worked, then we'd be so simple that we couldn't understand it. One of the amazing things that the human brain can do is pattern recognition. I'm not a paleo, what would that be? Studier of human evolution, but I do like to read stuff as a hobby. I am, after all, a PhD student. I wouldn't say waste, but I spend a lot of time reading stuff. One of the latest, meaning in terms of from beginning to end, near the end of where we are now. Developments in the human biology is this front part of your brain here. I think it's called the frontal neocortex. This is the part of the brain that allows humans to recognize patterns and plan for the future based on those. I think I was reading, I don't remember the exact amount of years, but that particular part of the brain lets us do things that no other species on the planet can do. So look at what we have here. We've got, that's too much. We've got a couple sequences, A, B, C, D, E, and then blank, 5, 10, 15, 20, 20, 25. And our brains are so good at doing this that it's difficult for me to not say what goes here just by listing it off. In fact, this kind of testing for pattern recognition, because these are patterns. What is the pattern here? What would the entry, yeah, Civ 5 is a good game, good quote too, yep. What would be the entry, oops, I'm using my stylus, I probably shouldn't do that. What would the entry for this first sequence be here? Does anybody know? According to what you've seen, you've been given 5 entries in this sequence. And that's the only rules of the game you can infer. But based on your knowledge and the sequence, what would you say comes next?
F.
Civ F. Yep, that's appropriate. What about here? What do you think comes here? We go 2, and then 4, and then 8, and then 16, and then 32, and then something. 64. Yes, that would be correct. This is doubling the number each time. Does anybody know what this sequence is? If you do, you get an imaginary cookie. What this sequence is doing is whichever element you are on is the sum of the previous 2 elements. And the first 2 elements are special. It's 0 and then 1. So this is the one where we start doing the calculation. 1 plus 0 is 1. And then 2 is 1 plus 1. And then 3 is 2 plus 1. And what would the next number be? Yes, it's the Fibonacci sequence. Very good. You may think that seeing these kinds of patterns and being able to answer these questions is trivial, but it's actually a very miraculous thing. Similarly, there is this image that I'm sure you've all seen in some form or another. I remember first seeing it, I think in like middle school, but it was an art class. This is the golden ratio. In that you have something with a length of A, and then let's call it a width of A and B. And the actual ratio is A plus B is to A as A is to B, meaning, let me get the annotation tool up, meaning that this length here and this length here have the same kind of ratio. Actually, they have symbols, so I don't know why I'm using X and Y. These two have the same kind of ratio as this segment does to this segment. And we see this all over the place in nature. In fact, some people posit that it's so common that we instinctively recognize it, as maybe we evolved that way. I don't know. But we naturally see it even when you don't know what it is, but you can superimpose it all over things in nature. How come we're so good at looking just at you can see this image we're looking at right here, the composite of what, 12 of these? And within a couple seconds, you can see, obviously they're here and arranged because they're all similar, but it doesn't take me telling you that to figure out, hey, there's some kind of spiral pattern going on here. And they seem to all be obeying this ratio that we've been talking about. That's kind of weird. Nature's weird, right? Why is the universe doing all these patterns? How come there's an image that comes to mind. Obviously, I'm not going to draw it. I'm terrible at drawing. Where it's a side by side of, I think it's like an X-ray mapping of the known universe, and it looks like just a bunch of weird connected causeways, and they're a bunch of corridors that are connected in some way. And so this is the mapping of the known universe. And right next to it is the neurons in the brain, and they look very eerily similar. Obviously, I'm just drawing lines here, but it's just a bunch of pathways of the connectivity and things in the macro scale of the universe, talking billions of light years. And the same thing, same kind of pattern appears in our brain in the electrical conduits. It's weird how many coincidences there are in nature. And what's even weirder is that we can see them. That's, at least to me, it's weird enough that the Matrix, you know, if we consider our world to be the Matrix, it's weird enough that the Matrix has so many, well, this brick has the same kind of algorithm coding as that cat over there. But what's even stranger and more miraculous is that we can recognize that. Depending on your perspective, the Matrix or the universe was created or became the way it is. But the fact that the people in the Matrix, the actors in the Matrix, can see those things, that's very interesting to me. So how does our brain do this? How do we do the guess / predict to get to the next part? Is it that there is only one possible option? Is it that we have the previous items? Or is it the relationship between the items? What if we have more than one sequence? What if we have two sets of numbers? How can we predict the next item in a situation like that? Hopefully, all this is ringing a bell from what we were talking about last time. Does the idea of the blue points and a red line, not a blue pill and a red pill, but having these fit together, does this sound familiar? Well, the thing we have to do now, it should be reminding you of, I think I brought the term up linear regression last time. If I didn't, I did at least said the line of best fit. This brings up a topic I like to touch on a lot. The stuff I was just talking about, how it's so miraculous that we can see these things and we can do it like that. I snapped my finger, but I got my glove on, so it didn't work. We have to be able to teach a computer how to do this. And the thing I like to point out a lot is that computers are stupid. They are dumb. They don't know anything, but they are lickety split fast. That's the trade-off we get, is that the human brain is able to filter out all the parts of this image here that aren't relevant to what we're trying to get across. But a computer doesn't know how to do that. You have to tell it how to do it. It's just faster than you can imagine. So if we can take this intuition of pattern recognition, try to formalize, how does my brain do this? I was able to predict the next 3 steps in the pattern, and I don't even know how I did it. Maybe if I can formalize the way I do that, the 5 minutes it took me scratching my chin to figure out the next 3 items, I can teach a computer to do it, and it'll be done in less than a second. So that's what we're going to be doing. Here's an example. We have some experimental observations. So on the left, we have a column of the elapsed time in seconds from 0 to 10. And on the right, in the right column, we have a measurement of speed in meters per second. So at 0, when we start out, we're not moving. We have a speed of 0. Now, here's what we want to be doing. Now, keep in mind that this is just I might actually, if I can make this work. This is the scaffolding for what we're wanting to do. What's a good color? Let's try blue. Actually, I can use text. So I'm going to try to keep this on the screen the whole time, but I'll make it shorter. All right. If it's going to be transparent, I'll make it something brighter. All right, let's try red. Okay, so one, we want to plot speed versus time, blue marker. I'll call it scatter plot because that's what we want, scatter plot. Okay, and that's the first thing we want to do. Two, we want to red line based on y equals mx plus b. Three.
Let me save you from some suffering. If you scroll down a little bit, it's already done.
Yeah, I know. Okay, that's
Okay.
fine.
I mean, unless that's your intent, that's fine.
I was just wanting to have it like on the screen that we can always remember, but it's not, it's transparent. It's kind of hard to see anyway. Now that I click off of it, it's not so great.
Oh, you were
But
just scaffolding it. I get it. I get it.
yeah, I was just wanting, like, if I could take this and cut it and just have it float around with us, that's what I wanted to do. But it's not worth taking the time because it's transparent and it didn't look too good. Okay, but try to keep in mind mentally what we're wanting to do. First thing we want to do is, well, we want these points to be visible. Well, what's a point? It's at least in a Cartesian plane. That might sound strange to you, but you've all used it before. What's a Cartesian plane? It's X and a Y. So this is a input. This is an output. X and a Y, X and a Y. So we want to plot those points. Let's use some blue markers. Then we want to put a line through them. Which line? I don't know. Any line we want. If they're all in a actual line, then it would make sense to put a line that goes through all of them. Let's try getting the M and the B, so the slope and the y-intercept, which provide a good visual fit. What does it mean to have a good visual fit? Well, we're just going to use our eyeballs. And then finally, using that data model, we want to estimate the speed at 15 seconds, which we don't have an observation for. Oh, wow, we've done this before. So let's look at a little bit of terminology. When we say linear regression, there's two words there. Linear, meaning a line, meaning no curve. It's just a straight slope, no change in the rate. And then regression. So what does that mean? Well, it is a predictive technique that we use to observe data and predict a value. We have to this a predictor variable, so that's the input. And these are the variables that will help predict the value of the output variable, commonly referred to as X. And then we have the output variable, it's commonly referred to as Y. This is the one we're wanting to predict. So to estimate Y using linear regression, we want to stipulate the following model equation. Now, this looks kind of funky. Why do I replace my nice and everybody knows this one, y equals mx plus b. So what am I doing replacing symbols for stuff? Well, it's because generally when we are doing linear regression or some kind of prediction like this, what you're going to have to figure out is what method do you want to use? And that's what we're talking about right here. What method do you want to use to say which line's better than another line? We'll explain that here in a second. Every time I clear, it draws another one. So a meaningful goal is to find statistically significant values of the parameters alpha and beta that minimize the difference between y naught and ye. If we're able to determine the optimum values of those, then we will have the line of best fit that we can use. So how do we estimate alpha and beta? Well, that's a good question. Well, so unfortunately in dark mode, this one's a little hard to see, but I'll switch to light mode real quick. Everyone prepare your eyes. There we go. All right. So we're getting into the subject of what does it mean for a line to be best fit? Well, what we're going to just use, there's a bunch of methods. In fact, you can think of, take a point on your scatter plot and your line and have the relationship between them be random. Take all the random measurements between all your points in your line and make that a number. You now have a method of seeing a line is better than another line. Is that method any good? No, probably not, because it's random. But this lets us talk about the idea that you can have whatever method you like. There are a couple that are pretty much well agreed upon as being really good. This one is called ordinary least squares. What are we going to do? Well, we're going to measure the distance between each point and the line vertically. So let me try to move my camera thingy so I can read everything. All right, so the objective of the least squares method is to find values of alpha and beta that minimize the sum of the squared difference between y naught. And this is the expected NYE. So the distance between the linear fit and the observed points. So we have our scatter plot, right? One second. I don't want the dog to pee on the floor. Okay, we have our plot. And, you know, it's got dots to it. And then I'm going to put a line here. And I'm just going to use my eyeballs to kind of try and make one. It's going to look a little bit like that. Now, what we're wanting to do in the least squares method is take every point and draw the distance. Well, you're not actually drawing, you're just measuring vertically from the point to the line you think is the best fit. Now, these lines are going to have values to them. So this will be some, I don't know, 6. This will be about the same. This will be 3 or something. You take all these, you square them, and then you divide by how many you have. And that's the formula we're showing over here. And what this will do is it will give you your beta, which will be your y-intercept, what we're talking about, and your alpha, which is going to be your slope. This isn't a, what do you do this in calculus? No, I think this is not a numerical analysis class, so we're not going to derive the equation. We're just going to use it. Okay. Now, in this equation, and this is common notation here, x bar is how you, at least how I know to say this from your algebra. So x bar is the mean of all the x values, and y bar is the mean of all the y values. Now, this formula here is actually called the covariance of two variables. Let's see. Reminds me of stats and Sarkis. Yeah. Yeah. I remember. Well, I won't go on that tangent. I'll go on another tangent. So x bar is the mean of the x, and y bar is the mean of the y's. Beta is the covariance of x and y, and so it's the covariance divided by the variance of x. So in probability theory and statistics, covariance is a measure of the joint variability of two random variables. Well, what does that mean? Well, think back to what is a random variable. I've got a coin. I say it's a fair coin. You're going to do an experiment of 10 coin flips, and you're going to tell me how many times that coin landed heads. So we don't know what that number is going to be. It's random. Let's assume it's random. The number you're coming back to me with every time you run an experiment, that's your random variable. So let's say I have two random variables. One is flipping the coin 10 times, telling me how many times came up heads. And so I give one person that experiment. Another person, I'm going to give another experiment. I'm going to give you a D6. And I want you to roll it 5 times, add up the faces, and come back to me with the average. Are those experiments dependent on each other? Does one affect the outcome of the other? I'll make it even simpler. So everyone in the class, I'm going to have a deck of 52 cards. I'm going to shuffle it, and the one person's going to draw a card. They're going to write down what it is, and they're going to put the card back, and I'm going to shuffle it. If you're the third person in line to draw a card, did the card that the first or second person get affect what card you're going to get? No, not if I shuffle it fairly. So in that instance, there's actually a term for this. Those random variables, what your card is going to be, are independent. Now, what if the person keeps the card and then I shuffle the deck? Does the first person and the second person's card affect what yours might be? Yes, it does, because if the first person draws the ace of spades and the second person draws the ace of clubs, there's only 2 aces left in the deck. Whereas from a fresh deck, there's 4. So the outcome that you're getting is affected. So we can talk about what the covariance of stuff is in the sense that it will tell us how things are correlated, if they're even correlated at all. So here we have some visualization of correlation. I'm going to read this definition for you. Hopefully that real life example helped a little bit. So in probability and stats, covariance is a measure of the joint variability of 2 random variables. If the greater values of one variable mainly correspond with the greater values of the other variable, and the same holds for lesser values, i.e., variables tend to show similar behavior, the covariance is positive. In the opposite case, when the greater values of one variable mainly correspond to the lesser values of the other, so high input, low output, or low input, high output, whatever you want, the covariance is negative. The sign of the covariance therefore shows the tendency in the linear relationship between the variables. What's a linear relationship? Well, I have my Cartesian plane, x and y, and if a line perfectly fits through every point, well, that's a linear relationship right there. But what if I move one of the points just a little bit? It's kind of linear. It's pretty close to linear, I would say. The more linear it is, the more linear it is, really. That's a terrible joke, but I think that's the best kind. If there is, as you can see here, 0 correlation, it essentially means that the points are as random as they can be. There's no correlation that we can infer, positive or negative. The magnitude of covariance is not easy to interpret because it's not normalized and hence depends on the magnitude of the variables. The normalized version of the covariance is called the correlation coefficient. It is shows by its magnitude the strength of the linear relation. So from the covariance, we can get the correlation coefficient. And this ranges from -1 to 1, 1 to -1, in which case you have on the one side as positive a correlation as I can infer. I'm pretty sure if you take the y equals x and plug it in with some data points, you'll get, that's a perfect line. Same thing for y equals -x. If you have a true random, I think we did this at one point. may have been the other lab. If you have some truly random points and put them on your plot, you're going to have a hard time getting a positive or negative correlation, and your correlation is going to tend closer to 0. How many more formulas do we have? Because this is burning my eyes. Okay, so the correlation coefficient definition, at least that we're going to be using, they're used in statistics to measure how strong a relationship is between two variables. There are several types of correlation coefficients, but the most popular is Pearson's. Pearson's correlation is also called Pearson's R, is a correlation coefficient commonly used in linear regression. These formulas are used to find how strong a relationship is between data. The formula for Pearson's R coefficient is here. Again, I suppose, at least I think this is a tangent worth talking about. This is a freshman class, so I will give just a little bit of advice. At least I hope you take it as advice. In at least the STEM classes, and I'm sure this applies to other stuff, there is essentially the engineer's version and there is the mathematician's version. The mathematician version of this class, we're going to spend the next hour and a half deriving this equation. We need to know how it's derived, the methods and tricks we use to derive it, so that in the future, when we see something, we can use those on our own and we're fluent in those tools. In the engineer's class, you take it on faith that the mathematicians that derived it did a good job. And if you're curious, you can look it up, but we're just going to use it. We don't need to derive it to use it. I don't need to know the innermost mechanics of glass blowing in order to use this bottle here. I'm just going to use the bottle. So this is an engineering class, as far as I know. So we're not going to be deriving anything like that. But here is the formula for the Pearson's R coefficient. Rarely, if ever, maybe a question on an exam would have you actually not derive it, but plug things in. But other than that, you're going to be using the actual, I forget the syntax, but it's just a function. And it's pretty easy. The formulas return a value between -1 and 1, just like we were talking about before. So the more it tends toward 1 or -1, the more what I'll call perfectly linear it is, either in the positive direction or in the negative direction. So the kind of what I just said is here, the correlation of coefficient of 1, and I should be a little more specific. You don't have a correlation of 1. You have a correlation coefficient of 1. So it means that for every positive increase in one variable, there's a positive increase of a fixed proportion in the other. For example, shoe sizes go up in almost perfect correlation with foot length. Why would that be? Well, sometimes you got to step back and take your engineering computer science cap off and put your common sense cap back on. Well, the foot goes inside the shoe and you want your shoe to fit. A -1 on your correlation coefficient means that for every positive increase in one variable, there's a negative decrease of a fixed proportion in the other. For example, the amount of gas in the tank decreases in almost perfect correlation with speed. So something that is worth highlighting, both literally and metaphorically, I guess, or rhetorically, I guess, is this term here, a fixed proportion. So I'm going to draw a positive correlation, and this is inside of my scatter plot somewhere. Don't laugh at my inability to draw correct 90-degree angles. All right, so let's assume that this is y equals x. Is the correlation coefficient always linear? A number can't be linear, so I'm a little bit confused. The correlation coefficient is something in the -1 to 1 inclusive range, but it can be anything in there. So maybe if you could rephrase your question, I might be able to answer it. So let's assume that this one is y equals x. This is the correlation coefficient here is going to be 1. If I get a value of 1, I get an output of 1. If I get a value of 2, I get an output of 2. Now I've got another line here. It's still a positive correlation. The correlation coefficient for this line, I don't really know what it is. It's just some y equals 1 over something, where alpha is greater than 1x, meaning that there's still a positive increase from input to output, but it isn't in the exact same proportion. An increase of 1 from 0 to 1 gives me an increase of 1 in the output. The same measure in input, and this doesn't have to be the same magnitude, but the same proportion of input gives me the same proportion in output. This line here, we don't have that. It's still positively correlated, but an increase of 1 might give me an increase of, I don't know, 0.7 in the output. Okay, so the question is does the correlation coefficient only work when the correlation is linear? Well, yes and no, because what we're doing here is we're choosing to make a linear correlation. So I've got my scatter plot, right? And what is my scatter plot? Now, since it's 2D, it means we have an input and an output. Just that's it. We don't have a three-dimensional. So I've got a plot of stuff, right? What do we want to do with this? Well, we want to do some kind of pattern, see if we can find a pattern here. I'm choosing to try a linear pattern. So since I have already made the choice to do linear regression, the only thing I'm ever going to be dealing with are lines. So the correlation is always going to be dealing with a linear system. No, it's a bad word because linear system is a real thing. It's only ever going to be dealing with lines because I chose in the world of problem solving with lines, you're only ever going to be dealing with lines. However, if you want to choose a polynomial regression or an exponential regression, they have their own types of correlation coefficients. I don't believe that the Pearsons works in the same in a polynomial regression. I don't think so, but I'm not sure. So the question you asked, hopefully that's a satisfactory answer. Anytime we're going to be talking about the R coefficient, we're already decided to be in the world of linear regression, so we're only ever going to be dealing with lines. Okay, so that is kind of the idea of what some correlation can look like. Let's look at an example. This is what we were looking at before. All right, now I need to turn this back because I am a programmer and we're all like Smeagol in his cave. Can't handle the light. All right. So we have some inputs and some outputs. All right. What do we want to do? Well, as we've done previously, well, let's look a little bit into the problem-solving method of what do we even do in this class? Well, we sure do tend to use a lot of data frames. Why do we want to use data frames? Well, they have a lot of nice stuff. All the nice visualizations, all the nice methods that we might want to do, they're already built in. So let's do that. Let's make a data frame. What are we putting in the data frame? Well, I've got some inputs for my time, and I've got some outputs for my speed. And they're all in numerical format. That makes it nice. And there's an equal number of them. So I'm just going to make a list of each. And I will make my data frame out of this? Can anybody tell me what kind of thing this is? The thing I have highlighted? It is a dictionary. Very good. I didn't even have to give hints. All right. So here is my data frame. It is all the stuff we were talking about, but now it's in the data frame package. Let's look at what we got. We have 11 entries for each. The mean time is 5 seconds. The mean speed is 43.1 meters per second. We've got a standard deviation for each, a minimum, a maximum, and our quartiles. Very cool. What else can we look at? Well, I know we want the variance. Variance is you're almost always going to use it. So what's the variance in my time and what's the variance in my speed? Well, it was already up. Oh, I thought it was. The variance of the recorded times is 11 and the variance of recorded, speed. Variance of recorded speeds, I believe, plural. Now, remember that variances can be weird in that how on earth is there a variance of 17,000 meters per second when that's 17,000, 1,700, when the highest speed we have is 121 meters per second? Well, there's two things you need to remember. One, the variance doesn't have a unit. It's just a number. And as such, since we're talking about speed and my variance isn't speed, you don't need to be surprised when the number seems kind of different than your other ones, especially according to magnitude. Okay. Is there a relationship based on covariance and correlation between time and speed? I don't know. Let's find out. If we want the covariance, notice that we don't have to give the covariance any random variables because we're using our data frame. Another nice reason to use a data frame. We have the following. We can use the correlation using the Pearson method to get that also. But let's look at this.
You just muted.
I did. Weird. Can you guys not hear me? Oh, Cole says he can hear me. Interesting. Well, people in the chat are saying that they can hear me, but all right. So interesting. What might, do these two numbers here look kind of familiar? We're talking again about covariances are still, you can consider they're the same kind of thing as a variance. It's a unitless numerical measurement. Where have we seen a kind of non-unit measurement of 11 and 1697? Does anybody remember? I think we've seen these two numbers before. Does anybody know? Yes, right above. They're right here. Why is that? Well, you have you've got a X1, X2, Y1, Y2 situation going on here. It just so happens that the X1 and Y1 are the same thing. So if I'm getting the covariance of time is a random variable, and time, what's the covariance of these two? It's the variance of itself. Taking the covariance, what's the best way to say this? A random variable's covariance is its own variance. So that's why when we plug in our covariance formula for time and time, we get the variance for time. And why we have the same thing for speed. Now, remember, that we had that formula here, or we had the formula above. It's probably going to be all weird looking now because I switched back. But we have a covariance between time and speed, speed and time, time and speed. I think sometimes it might matter the order, but it doesn't here, and doesn't in most cases. We have a covariance. Okay, cool. That's nice. What does it tell us? I don't know. Covariances are, variances in general are hard to interpret. They don't even have a unit. So let's talk about the correlation. So we're going to use the Pearson method to find the correlation. Now, what's the correlation of time and time? It's 1, obviously. If I have an input on my x, y Cartesian plane, and I'm going to make the output the input. Okay, well, you have y equals x. So the correlation between a random variable and itself is 1. But the interesting thing that we're actually wanting to look at is the correlation between time and speed. So we get a correlation coefficient of 0.96. Sorry, I got an email that broke my train of thought. 0.96. So can anyone remember what is the range that a correlation coefficient can have from what to what? 0 to 1. Are you sure? We can go from -1 to 1. Negative meaning that they are negatively correlated. So from -1 to 1, and we had a correlation coefficient of 0.96. So if a 1 is perfectly, I'll just say positively correlated, and -1 is negatively correlated, and 0 is everything's random, what would you say 0.96 is? Just in English. Is it perfectly negatively correlated? It's like 2 adjectives on 1 noun. Very high positive correlation. Yep, I like that. A 0.96 is only what, 0.036 off from just a pure straight line. But this is kind of what we were talking about before with the gas and the tank and the speed. This is one of those examples that has a pretty linear relationship. Let's do an actual linear regression now that we've talked about all that stuff. So we want to estimate our output using our least squares method. So we need to calculate the mean of the x's and the means of the y, the covariance of x and y, and the variance of x, before we can determine our alpha and our beta. Why do we need to know all that stuff? Well, it's because it was in the formula, which is here. And I will blind myself again to remind it. All right, so remember we need our x values, our y values, the mean of our x values, the mean of our y values, and that will get us our beta. And for the alpha, we're using everything we had before and the beta. And something worth noting is that beta is the covariance. So that's why we need the covariance. All right, so let's actually calculate that stuff. And again, why do we use our NumPys and our pandas? Well, they let us do a whole bunch of nice things that wouldn't be too hard to do. All right, let's get the means of our time and speed. All right, we're also going to get the terms needed for the numerator and denominator of our covariance, which was beta. So what was in the numerator? We had the actual for each time element, subtract the average, and multiply that by, for each speed element, subtract the average of the speed. And then we have the same thing here, but squared. Okay, so that's the other part we need. And then put all the pieces together. Beta, I want the sum of all the covariance things we're doing above divided by the sum of all the X variance stuff below. That's the formula again. This one that's kind of hard to see. So we've got two sums, and the top sum is element minus X average, X mean, times element minus Y mean, and the bottom part is a sum of element minus X mean squared. It is the least squares method. All right, let's run this, see what we get. Okay, so we have an alpha of negative 16.7-ish and a beta of 11.9-ish. Okay, now what did that do for us? Well, remember before when we talked about making a line, y equals mx plus b, except we're going to say y estimate is alpha times, no, I'm sorry, beta times x plus alpha. Well, let's do that. All right. So this is going to be the outputs for what we're predicting with our predicted line, our predicted linear formula. Let's plot some stuff. Now, if you think back to the start of this, we had a list of like 4 things we wanted to do. Well, now we're actually, well, we're almost done with it, to be honest. But we wanted to plot our speed with some blue scatter point. We did that. And if the red line weren't here, I think maybe we actually used this data before. We'd be playing the game of, make it red. Well, let's try to make a line. That one looks all right. Does the first one look better than the second one? Yeah, I think so. We'd be playing this game visually to try to get a line that kind of goes through them all as best we can. Obviously, you can't go through them all because a line won't fit them. But we're using the least squares method to get this. So the red line is our line of best fit. We can see from the graph that there's a positive linear relationship between x and y. And using our model, we can predict y for any value of x we like. How is that? Well, we have a formula here. This is our model. So for example, if we have an x value of 20, and I want to know what our speed would be, unless some wonky stuff goes on, like, I don't know what speed we're measuring here. Let's see, meters per second. That's pretty fast, isn't it? So whatever vehicle this is, because I'm pretty sure it's not human, its true relationship is something like this, unless something wonky, like, I don't know, a sound barrier or something happens like right here where things we're seeing that we're not predicting, because we're predicting this line goes just up and up and up and up and up. Unless something weird happens, we can predict any value we want. So let's predict for 20. What do we get? Well, according to our estimate, at 20 seconds, we should be going 222.75 meters per second. And my metric's not super fast, or super great, but I think that's pretty fast. That's 2 football fields-ish. That's fast. All right. So that was all the insides of how we do a linear regression. But we have packages that can do all that. So let's use the stats models package. Now I did not, let's see, is this the line? There was a line in here somewhere where there could be an error, but I didn't get one. So, and not like an error in the code. I mean, might need a new package, like to install some stuff. All right. So the syntax here is a bit clunky, but here's how we're going to do it. Clunky because this is a little. All right. So we want to get the stats models package. We're going to call it SMF, and we're going to initialize and fit linear regression model using stats models. All right. I'm going to make a variable. My SMF has this OLS function. And what we're going to do is give it the correct constructor syntax and run the fit method. We no longer have to calculate alpha and beta ourselves, as this method does it automatically. Now calling params will show the parameters. Intercept at -16 time 11.9. And the notation we've been using, alpha is the intercept and beta is the slope. So we have what we calculated before. Let's see, how close was our manual method? -16.78 and 11.97. It's almost like we're using the same method. It's almost like that's what OLS means. Okay. Here we're going to replicate the process, but using values from the model object. All right, so we've got our prediction off of we made model here. So we're going to call the predict method from our model. And we're going to say this is our speed prediction. And this is just a bunch of plot stuff that everybody should be used to by now. So let's show it. So we have pretty much what we had before. So how good do you feel about this predictive model? Will you trust it? So let's say these are the measured velocities for, I guess it's just speed, not velocity. These are the measured speed for, I don't know, an escape pod on a space station. You know the velocities for the first 11 points. And if your prediction, so your predicted regression is off of the true value by more than 10%, you die. Moreover, you need to have the prediction of time at 60 seconds. Do you trust this model or not? Do you guys trust the model at 60 seconds? No? Why is that? It visually doesn't appear to be linear. I tend to agree. I think there's some kind of maybe quadratic thing going on here. But what we can say is that well, it is the line of best fit for the data. But what we can say is that the further you go on in time, the less accurate it'll be. So it depends on at what point are you talking about? 11, 12, 20, maybe. 60, probably not. Okay, another example. This is definitely a real life example of we want to predict stuff. Here's the idea. We have a data set of spendings on TV, radio, and newspaper advertisements, and a number of sales for a specific product. We're interested in exploring the relationship between these parameters and answering the following questions. So, spending on advertisement for TV, radio, and newspaper, and purchases of TV, radios, and newspaper. Well, it's not buying the actual TV, radios, and newspaper. It's I'm putting out an ad on TV, I'm putting out an ad on radio, I'm putting out an ad in newspaper for widgets. And then we're measuring how much widgets we sold. Okay, so can TV advertising spending predict the number of sales for the product? Same question for radio and newspaper. Can we use the three of them to predict the number of sales for the product? Which parameter is a better predictor for the number of sales for widgets? Well, let's find out. We've got a CSV. I already ran this, so it should already be there, but we can run it again. Let's see what it looks like. Advertising. All right. Have pretty much what we would expect. This is measured in dollars, I would assume. The amount of in advertisement budget for TV advertisement, radio advertisement, newspaper advertisement, and the sales for that period of time. Okay. We got that. Let's see what, well, that's kind of what I just looked at. This is the one I was interested in. See what's some facts about this stuff. We got 200 entries. The mean budget for TV advertising is 147. Who knows what this is? Could be millions of dollars, could be, who knows? But they're all the same unit, so it doesn't matter. So the mean advertisement budget for TV, 147, radio's 23.2, newspapers 30.5, and the mean sales for that period is 14. We got our standard deviations, which are useful. And we got our quartiles. So the maximum was 296. Okay. We can put these series into variables. And now what we're going to do is talk about the covariance of one versus another. Now, remember, as we had before, we had the, I don't know the term for that. It's the, I want to say truth table kind of thing, where you've got, you know, this one versus this one versus that one. I'm sure there's a name for it. Let's look. So what is the covariance of the TV advertisement budget with the TV advertisement budget? It's just the variance. But so now we can see anything that's not on the diagonal is worth looking at. And you notice that this is a symmetrical matrix. What does that mean? It means that the lower triangular part and the upper triangular part are reciprocals. So this one and that one, this one and that one, this one and that one. Okay. That's all well and good, but variances are hard to read. Let's talk about the correlation coefficient using the Pearson method. Obviously, the diagonal, everything is perfectly correlated with itself. Let's see. The TV advertisement budget has a 0.05 covariance with the radio advertisement budget. So what would you say in English about the correlation between the TV advertisement budget and the radio advertisement budget? It's no good. It depends. What would you call no good? Very weak. Okay, I'll accept that. The correlation is weak, meaning they're almost completely random to each other. They aren't really correlated. They, if I don't know if this is entirely accurate, but I would think so. If the correlation coefficient is 0, then they are independent. They have no bearing on each other. So this is pretty close. Same thing with newspaper. The correlation between TV and newspaper don't seem to have much in common. What about this one? What would you say in English about the correlation between TV budget and sales? What do you guys think? 0.78. Yeah, that one is a pretty good positive correlation, at least compared to the others. I would say so. It's definitely the most positive of them. 0.78 is more than halfway between 0.5 and 1. So I'd say it's close-ish. Let us see if we can answer the first question. Can TV advertising spending predict the number of sales for a product? Well, if we're going to predict it based on any of these, I would have to say yes. It's at least more than 0.5 positively correlated. Okay, so let's assume it is, that we can use it. we have our alpha and beta that we were going to use to try to make a best fit line. Let's make our plot. And this is the prediction with the only using the TV spending. So TV advertising spending is the x-axis and the y-axis is the sales of our widget. I mean, I can kind of see that line, at least visually, it doesn't look horrible. So I would say, yeah, we can use that. I mean, it's just a gut call. If you want to formalize a way to say, is this a good fit or not? We can do that, but this is an engineering class. I would say, at least visually, it looks pretty good. So, yeah. How about using the radio advertising? Remember, what was the correlation between radio and sales is 0.56. So if we consider, 0 is completely random and 1 to be perfectly correlated, we'll call 0.5 to be halfway between there. It's on the correlated side of halfway, not by much. Let's see what it looks like. So this is the line of best fit if we only use radio spendings. Now, visually, I can definitely say this one is a better fit. Keep in mind, how are we doing this? We're measuring the distance and taking the squares of everything and summing them together. Whichever one has the minimum, that's the best one we want to use. This one, I can see what it's getting. There's kind of a pattern here, but there's more of a scatter, no pun intended, around it than there is here. Not as closely, the grouping isn't as tight. I mean, we can use it if you want. Can radio advertising spending predict the number of sales for the product? Sure. Not as well as TV spending, though. Okay, well, let's try the newspaper advertising, which had the lowest correlation of them all. It's the closest to completely random that we have. Let's see what it looks like. All righty. This is one of those situations where when you're handed just a straight linear regression model, a prediction, one of the very first things you need to ask is this a good fit? I suppose it's a bad word. Was using my linear regression least squares method a good idea for my data? Not here. The items we're looking at don't appear to be correlated enough for it to really be that useful to me. This seems like a complete scattershot. So it looks almost random. So I don't think this one's very good for it. Not really. Okay. So for this next part, I didn't have an issue doing using the sklearn package. You may, and if you do have an issue, run this for Unix. For Windows, I didn't have to do anything, so I'm not sure. Now, what are we going to do? Well, remember, we wanted to answer the question here. Well, I've used each of them individually, but let's see if we can make a multiple linear regression model. All right, so this is a package, so you don't really need to know the inner workings of it, just the syntax of how to use it. What would a linear regression model look like? Well, it's in the comments here, but I'll try to give it a little bit of an explanation. So our formula for one input, one output, we had y equals mx plus b, right? Well, what if I have more than one input in my linear model? Well, I have y equals m1 x1 plus m2 x2 plus b. And what if I have 3? What if I have so on and so forth? That's what this formula is here. And the actual formula we're going to be using is this one. I think that's a sigma. No, it's going to be a theta. Anyway, it doesn't matter. All right, so let's try to make that formula with our sklearn package. So here are the predictors we want to talk about. My x-axis, I want it to be the predictors. My y-axis, I want it to be the output, the sales. Do linear regression, and our linear regression fit on x and y. Okay, done. Let's print them out. All right, we've got an alpha. Remember, we had the intercept, and we've got betas. Alpha of 2.9. And these are the betas we have here. So our model is now, remember we have X1, X2, and X3. Those are TV, radio, and newspaper, respectively. So our formula looks now like this. We can predict the sales from any combination of TV, radio, and newspaper advertising costs. For example, if we want to know how many sales we'd make if we invested, let's say, $300 in TV advertisement, 200 in radio, and 50 in newspaper, all we have to do is plug it in. This is our estimation for what we would sell in widgets given our advertisement budgets. So, final question. Which parameter is a better predictor of the number of sales for the product? Which budget? TV, radio, or newspaper? What do you guys think? TV, why is that? TV, bunch of TVs. Why is that? So while you guys think of an answer of why, I will share a little way you could, I guess, prove it if you want. Let's say I'm going to change one of these values. I'm going to cut it in half. My original value was 54. And I'm going to change this to 150. And I went down to 47. So by changing that, I go down that much. Changing that, I go down that much. Changing that. I didn't even change much at all, did it? This isn't a proof. It just gives you an idea of, well, which one of these is more important to have. If I were asked the question, yep, that's the one. It has a bigger positive correlation coefficient. So what does that mean? We can infer from the betas. These are the betas for TV, radio, and newspaper. Well, surprise, that one's higher than that one. That did kind of make sense, though. This one, surprisingly, I'm surprised that changing this changed the output the most. So I didn't expect that, but that's what the numbers seem to show. And that is what the beta of the newspaper, I'm sorry, radio, not newspaper, radio budget seems to show. But again, we're using unequal values here. If you really wanted to get the experiment down, put the same thing in each of them, 100, 100, 100, and then start tweaking one at a time and see which one changes the output. So what can we infer from the betas? We can infer that the change in output for sales, given changing of the input, one or more, is influenced by the coefficient in front, which is the beta. And you can infer a lot more, but let's see. We got a couple minutes left. So I'm going to look at the homework real quick. It's just doing what we did. The only thing we haven't got to would be the multiple linear regression, which I'll show in a second. But the thing I want to point out is what I was kind of trying to do earlier, in that you have a scaffolding here. What's a scaffolding? Well, it's the thing you stand on to do construction work. So Dr. Cleveland just said, I'm describing what is called a sensitivity analysis and is routinely a part of data science with respect to prediction. Yeah, so that's cool that it actually has a name. Believe it or not, this is a skill I just learned in video games. I got a puzzle and I got 3 things in front of me, or it might not even be a puzzle. I might be trying to sell stuff on the auction house. I change one, see how much it changes, change the other, see how much it changes, measure the difference in changes based on my combinations, and you're trying to maximize profit. So the thing I want to impress upon you is use the scaffolding. If you could make it a sticky note and have it next to your vision the entire time, because you always need to be thinking about step by step. All right, what's the next thing? What's the question I'm actually trying to answer? Why am I 16 layers deep in a MATLAB package trying to figure out how the syntax works, and I've completely forgotten what the original question was? Don't let that happen to you. Okay, let's look at our example for multiple regression. I'm just going to go through this pretty quick because we've only got a couple minutes. So the sklearn example is a multiple regression example where there's multiple input. We can use it in a little trick to improve our time speed example. So the thing we did first. All right. So we're going to do what we had before, but remember I said there's like a space pod ejection example. Let's see if we can make a better fit. We're going to add a column to the time frame. Okay. So we've got our time speed, and now we've added this time squared. Let's modify the model a bit. Let's see, initialize and fit. Okay, so we're just adding the time squared. So the predictors are not just time anymore. The predictors are time and the time squared. So what do I mean by time squared? Well, what's my my time is going up instead of in a linear fashion, so 0, 1, 2, 3, 4. It's going up in a squared fashion, I guess. It's at least polynomial. So 0, 1, and then 4, and then 9, and then 16. Let us, hey, look at that. So if you had to choose between, you got 2 prototypes for your escape pod, and amongst other things, you see that their predictions for type A looks like this, and type B looks like this. And it's your butt in the literal hot seat. Which one do you like? I like this one. So this part I really liked. I don't know if I have time to give it justice though. Oh, we'll try. So what did we change and why did it work so well? We'll consider the polynomial data model we had right here. So if you've got, y equals x squared plus 3x plus 2, you're going up to x2, beta 2, x, beta 1. And really there's an x0 here, but it's 1, so it doesn't matter. This is a polynomial, in-level polynomial. One way to fit this model to data is to construct a matrix comprised of observations and ones, then construct a linear system related to this design matrix. The data model is as a linear system looks like this. So X is a matrix, we have a coefficient matrix, and we have an output matrix. And they're vectors, but not important. So for the example, the polynomial model 2, call it order. So we have, x to the 0, which is 1, and x to the 1, which is x, and x to the 2, which is x squared. That's what we've got going on here. And then our coefficient vector and our, it's kind of weird, our y vector. Define the unknown coefficients, because we have our input measurements, we have our output measurements. To find the unknown coefficients, which is the solution of the linear system, we get what is called a best linear unbiased estimator fit. Now, this is some linear algebra here. I'm pretty sure you guys don't need to know it, and 2 are probably confused by now, but I love in linear algebra. That's why I think this is so interesting. This T stands for a transpose. So take the items that are on the opposite sides of our diagonals and swap them. Put a mirror down the middle and swap them. So we're going to do some stuff with a transpose on either side of the equation side, or the equality symbol. So remember that if you've got an equality, you can do the same thing to both sides. So I'm doing an X transpose to both sides. And then I do a little magic by just moving things around. I'm literally moving this over to the right. And now I have my coefficient vector is equal to this times this. And you do a little more math to figure this out. And there's a nice trick you can do with transposes. And you get what we had before. It's funny, I was using the escape pod, and the example here is about a ballistic missile. I like linear algebra. This is using the stuff we just talked about to predict the burn time for a ICBM. And that's a pretty good prediction. So, moral of the story for all this fancy linear algebra stuff, why would I ever want to do that? I can just draw lines. Because since this works and is sound, the method you use for a line to say get the best fit is the exact same method you use to do nonlinear stuff. The exact same. It's just that instead of using one thing, you're using a system. And the nice thing is the package does it mostly for you. All right, that was almost perfect timing. We are at 10:50, and that's my time. Dr. Cleveland, if you had any announcements or anything, I am done.
Okay. Okay, can you all hear me?
Yep.
Okay, cool. I'm gonna turn on my video real quick. I'm going to share my screen real quick, and then we will end the lab. So here's what I wanted to show when Blackboard wasn't working. There's this link to the semester project teams. If you take that, here are the team lists. So far, as of today, I only have one team that has given me their team members. So the remainder of you all identify fellow students in the class. I believe you can do that through Blackboard and the Texas Tech email and put together your teams. It may not be 16 this semester, but that's how much I've allocated. And as soon as you know who you're going to work with, send me an email so I can update this project team sheet. The project is largely what you have, all the tools you need as of today to be able to complete it reasonably well. There's some research on your part to do it great, but reasonably well, you have all the tools you need as of today. So with that, I will end the lab and thank you all for your attention. Have a great weekend. I don't think I've made an uploader for this lab yet, but I'll have that in the next few hours. So take care and thank you all again. Bye-bye.
Yep. See you guys.